let's get started. So we are now going to start to talk about strategy for integration, because we've learned a whole bunch of techniques, and now we're going to just have them at hand to take on whatever problem we see with respect to integration. So we've been studying all individual sections, focusing on one method or the other. I'm going to outline a strategy for you, how to approach a general integration problem. Then we're just going to do some. And you're going to have to just look at the problem and try and identify which tool you want to use to make progress with this. Sometimes there'll be more than one tool which is necessary. So this is section 7.5, strategy. And I'm going to outline for you a strategy to apply when you see a general problem. So the first thing is to see if you can simplify. So often there'll be some, well, not often, but sometimes there'll be some algebra which you can just do, which will turn a difficult looking problem into a rather easy one. So here's an example. Suppose we have something like this. We have the integral of the square root of 1 plus square root of x dx. We're just going to multiply through by the square root. And now this is an easy problem. These are just powers of x, right? So before you do anything, see if there's some simple algebra to do. Here's another example. If we see some kind of trig integral like this, before launching in with all our tan, sec type methods, just see if this isn't something that we can do more easily. So we know what tan is. Tan is equal to sine theta over cosine of theta. Sec is 1 over cosine of theta, so this is cosine squared of theta right here. So when the cosines cancel, and this is sine of theta, cosine of theta, like this. And then this is by this double angle formula. This is equal to 1 over 2, the integral of sine of 2 theta d theta. And this thing we can just integrate, right? Just ask ourselves, what do we differentiate to get this? And the answer is minus cosine of 2 theta divided by 2 plus a constant c, right? So no need to do difficult things here. When you simplify the expression, you get something you can actually do. Maybe just a final example. Let's label these guys 2, 3. If you see something like this, if we just multiply this stuff out, what we're going to see, we're going to have a cosine squared, we're going to have a sine squared, so we have cosine squared of theta plus sine squared of theta plus 2 sine theta cosine theta d theta. Cosine squared plus sine squared is just 1, right? So this integral of 1, and then this 2 sine theta cosine theta, we're going to use this identity we just used, that 2 sine theta cosine theta is just sine 2 theta. So then this is this thing. And it's something we can integrate, so it's easy. So before anything, just make sure that you're not actually looking at an easy integral that doesn't require any difficult techniques. Examiners love to do this. They love to present you with something that looks hard, where if you think about it before you try any method, it turns out to be easy. So stop before you do anything. See if you can just turn this into an easy integral by just messing around with it a little bit. Okay, once you've done that, once you've checked it doesn't just reduce, then you can try and classify what kind of problem you're looking at. So that's the step one. Maybe we call that step A. I'm using numbers already. No, I'm already, yeah, let's call this A. Try to simplify. Then B. Classify. The integral. So we've learned a whole bunch of methods, and we're going to try and classify what kind this integral might be approachable with. So the types we've learned, for example, it could be a trig integral. It could be just sine to some power, cosine to the power, sec to some power, tan to some power. It could be something that wants you to do integration by parts. Oh, can everybody who's here write in the chat here so I can see how many of you attending the live class? Could be integration by parts. It could be a rational function. And then we have to use this method we just learned in the last section, this partial fraction method. It could be a radical. And if it's a radical, if it's something like this, if it's plus or minus a squared plus or minus x squared, then it's a trig substitute. Okay. Or if you have just something like this, some root power of ax plus b, then try u sub. And I often like to let u be this guy because this is what I call a linear change, because the du is basically the same as the dx, just with an a in front. So this is a very easy u sub to do, very easy change to make. Or it often works to take u to be the entire radical expression and work with that thing. And that is your classification with respect to the various kind of methods that we've learned. So see which category it seems to fall in, and then simply try something. And it might not succeed. You might try something, it gets to a more complicated expression, doesn't seem to be simplifying. Then it could be you've made a completely wrong choice and you go back and you try something else. You know? Or it could be somewhere along the stage where you're working with it, it turns into a form where some other method can be applied. And if you look back at your steps, you'll realize that. You know? So if you do all this thing, then C, try again. You can't solve the problem by just looking at its form, finding the right form, then try again. Use a different method, maybe do some other algebra, maybe you missed a simplification. Maybe try u sub. Maybe that turns it into a different form that you can understand. Or try an integration by parts, and then it turns into a form you can understand. So I'm going to write integration by parts by I by p. Okay, and hopefully it will be something you can actually approach and make progress with once you do this. So think of it this way. You have a toolbox now. You have a toolbox of different techniques. And we're going to just present you with an integral. And your job as a craftsman is to pick the right tool to approach the problem and then apply it. And picking the right tool, or the right sequence of tools, is just a matter of practice. So the more you do these kind of things, the more you're going to find the right tools. Obviously, we can set up some really tricky integrals where you'll have to use multiple methods to actually get through. Yeah? So when you first are doing this, you can be quite stuck for a long time. You can look at quite strange expressions and go, okay, nothing I know is any use, but you try it. You try something, and then obviously all the problems you're asked do have a solution. So one of these things that we've taught you will work, or not one, but some sequence of these things. Yeah? And that is what gives this entire section value, in my opinion. So on the introductory video, I went on some kind of lengthy explanation about how we're transferring this learning of mathematics from the practice of algorithms to the learning of concepts, and talked about why that's a worthwhile thing to do, and why learning algorithms isn't a particularly worthwhile thing to do. This stuff is learning algorithms. This is an algorithmic section of the course, but I do value it nevertheless, because it will teach you firstly the language, and it will also teach you the process of solving problems inside the language, because many of these things can't be just done by routinely following a sequence of steps without thinking about it. You're going to have to learn the practice of seeing a problem, applying some techniques, not succeeding, backtracking, trying something else, maybe not succeeding then, but through your repeated efforts, learning things about the problem until you can succeed. So that is a valuable thing to learn. You're going to have to learn to be persistent, and you're going to have to learn to not get stressed and not get overwhelmed. Just keep calm and work your way through with the things we've learned. You're going to learn problem solving. And that is the value of this stuff. If I was math dictator of Cincinnati, and I would still teach you this stuff, even though it isn't important, it isn't something you're going to use in your future lives. You're not going to be using these techniques to solve integrals. You will put them into software like I do. I have to do calculations in my research work all the time. And it's very rare I'll actually look at a difficult integral, which I can't do in a second, and then go, okay, let me try this sequence of methods. I will just put it into software. There's so much software. It is good software. I don't have to think about it. But it's nevertheless worthwhile going through this, learning this, learning to solve problems, learning to persist, learning to go through difficulty, and learning to express things in this language. So this might not be enjoyable if you are starting this and you're struggling with it, but it's a craft, and you will get better at it as you practice. So that is what we will be learning in this section 7.5. We will just be looking at different integrals, and we won't be given which method to apply. We're going to have to come up with it. We're going to have to come up with it. And if we find the right methods, we'll succeed. And if we don't, we won't succeed. Yeah? Cool. All right, let's give it a go. Example 1. Tan to the power 3 of x over cosine to the power 3 of x dx. Okay, so solution. Is there any algebraic thing here that is going to simplify this, clarify what kind of form it is? Is there anything you can see, any suggestions you have for me? How would you want to simplify it? What would you like to do? Yeah, we could get into the terms of sine and cosine. Let's see what happens then. So someone else says secant and tan, yeah? So we could either put it in terms of sine or cosine, or secant of tan, yeah? Because we know that if we have integrals in terms of sine and cosine, or secant of tan, then they're trig integrals, we have a chance. Let's look at both. Let's see which one we prefer. So turn into sine and cosine. Then let's call this guy star. Becomes the integral of sine to the power 3 of x over cosine to the power 6 of x dx. So that's option A or option B. Turn into sec tan. If we turn into sec tan, sec is 1 over cosine, so we have tan to the power 3 of x sec to the power 3 of x dx. So that's B. Okay. Which do you prefer? Do you prefer A or B? Which looks better to you? Put your hands up like this if you prefer A. Put your thumbs up like this, I should say. Put your thumbs up like this if you prefer B. Most of you prefer B. And I prefer B too, because this thing is a sec-tan integral. The powers are positive. Here we have a negative power. Would I have to think about this? You could actually push this through. This would actually work, but I slightly prefer this form. Yeah? So if we look at this guy, we now know what form we're going to apply. It's a sec-tan integral. We either do a u sub with a sec or u sub with a tan. Those are our two choices. And we backwards engineer what form we need. Yeah? And if we do a u sub with a sec, yeah, then we have to pull out a sec-tan and then turn everything else into sec. Yeah? And if we do a u sub with a tan, we have to pull out a sec squared and turn everything else into tan. Yeah? Look at this. Which option is better? Do a u sub with sec or u sub with tan? Someone says sub with sec. What does everyone else think? Is that right? Do it like this if you wanna do a sub with sec. Some of you. Looks like most of you. Yeah, to me it looks like that's the easier option, because if I pull out a sec tan, then I have tan squared, sec squared, sec of x, tan of x, dx, right? And I have my identity that sec squared of x equals 1 plus tan squared of x. So I know I can turn this tan squared into 1 minus sec squared. And I can turn this entire guy into just 1 minus sec squared of x and sec squared again. Did I do that wrong? Did this over here? That's right, I did this wrong. Thank you very much. That's right. That's 1, like this. And this guy is our sec-tan. So this stuff is everything which we turn in terms of sec of x, tan of x, dx. And now we do this u is equal to sec of x, and then du by dx is equal to sec-tan. So we're going to do it like this. And then everything turns into u, right? So then we have u squared minus 1 u squared du, which is just a polynomial in u, right? This is u to the 4 minus u squared du, and there we go. Right? I mean, this, now it's routine, right? It's u to the 5 over 5, u to the 3 over 3, plus constant c, we put stuff back, and then we get sec of x to the 5 over 5 plus or minus sec of x to the 3 over 3 plus constant c, and there we go. Cool. Everybody happy? Yeah? So what did we do? We looked at this thing. We wanted to make some kind of algebraic or whatever simplification to turn it even into a sine cosine or a sec tan. Sec tan looked a little bit easier. Sine cosine would also have worked. Yeah? If it was sine cosine, we'd turn everything into either cosine with one sine or sine with one cosine. We could pull out one sine here. We'll have a sine squared. We replace that by 1 minus cosine squared and put it into here. Yeah? And then we would have an integral all in terms of cosine with one sine, and then we do a u sub. So we could also do that guy, but we don't want to deal with negative powers unless we really want to, or unless we really have to. So this is the easier form. Cool. All right, let's do another one. Example 2. What about this? Integral of e square root of x dx. Okay, suggestions. What do you want to do with this? Is there some algebraic simplification we can make, turn this into a different form? There isn't, right? This isn't a simple form. There's nothing to do here, right? Yeah? Okay, so we have one suggestion. Someone else, give me another suggestion. We could try integration by parts. What else could we do? U sub with what? So on the strategy list, one of the suggestions was when we see a radical, we just try and let u be the radical, see if that makes it better. Because radicals are a pain. These are things that are difficult for us to deal with. Yeah? So our first attempt might be to do that. Just see what happens if we let u be square root of x. So if we do that, what happens? Then we have du by dx is 1 over 2. X to the minus 1 over 2. Yeah? So we're going to have to turn stuff. We have to find the dx to replace this dx, right? So then this thing implies that 2 square root of x du is equal to dx, but this is actually u itself, right? So this is 2u du equals dx. So dx gets turned into a more complicated expression, but in exchange, we get rid of the square root and we just have a u. And that's worth it to us. We'd rather not deal with the square root even at the cost of a slightly more complicated thing here that replaces the dx. So then this guy, well, we'll see if it's worth it. Let's see what form we get. This guy turns into 2, pull out the 2, e to the u du. Is that progress? Is that a better form? Do you like that more? Yeah? All right, someone else is... There we go. This thing is a classic integration by parts problem, right? Because... Let's write this as equal to... Because we see that if we let this thing here be the v prime, and well, this thing is already u, and then we let this thing be the u, then if instead of dealing with v prime u, we deal with v u prime, we are in a better situation because v prime going to v makes things no worse because the antiderivative of e to the u is e to the u. E to the u never gets any better or worse when we integrate or differentiate it, right? Whereas if we differentiate u, we go from u to just 1, which makes it better, makes an easier expression, yeah? So then this guy is definitely something we want to use integration by parts with. You all see what I mean, huh? Yeah? Cool. So I'm going to replace this thing here by vu, so it is e to the u minus the integral of e to the u, which is v, and then u prime is just 1 du. This thing gets replaced like this, and then this thing is just 2 e to the u minus e to the u, and then plus a constant c, and then let's put things back in terms of guy. So we have 2 e to the square root of x minus e to the square root of x plus constant c, and there we go. Everybody with me? Yeah? All right, anything unclear? Do this hand gesture. All right, looks like everybody's good. Yeah? Okay, let's recap the steps. Recap the steps. What did we do? We saw this guy. We realized we see there's a square root. We don't like square roots. One of the prescriptions, one of the suggestions in the strategy is just to let u be the square root. Yeah. We try that, and we get to this form, and then we go, okay, well, this form is definitely better. We have an idea what to do here. We do integration by parts, and then that just does. Yeah. So we're doing exactly the strategy. We are trying something. It does indeed turn into something better. A suggestion right at the start was integration by parts. That maybe is reasonable. We could have tried that, and it would have probably not given us something as easy as this. Yeah. In many cases, there's more than one method, but there's nothing wrong if you try something and it doesn't work out. The key is not to get stressed by it, not to be annoyed. That's the process. You try something, you backtrack, you try something else. Yeah? You have to learn to accept that something you've tried, maybe spent 10 minutes on, 15 minutes on, tried hard, isn't necessarily going to be the right thing. Just have to give up on that, that work. You've learned something from it. You've learned that method's not making anything better. And then you try something else. Huh? Cool. All right. Let's do some more. Let's do this example. Example 4. So at the end of the book, there is a whole bunch of sections. At the end of each section, there's a whole bunch of questions, as you know. As extra practice, I recommend doing those. Particularly the odd-ordered exercises have the answers so you can see whether or not you're right. So I was doing some last night, and we'll hopefully get to that later. And they're actually pretty hard. They're not that easy. So if you do these extra practice problems, and I do recommend it, and you find them difficult, they are actually difficult. They're not. This is one of the harder sections we're going to face. Don't be put off, however. Do try them. Do give them a go. It's definitely good practice. Okay, look at this guy. Let's have someone who hasn't spoken yet. Is there any algebraic simplification? Turn this in a different form. All right, cool. Is there any algebraic simplification, people? Yeah, it doesn't look like it, right? There's nothing we can really do algebraically to this to turn it into a different form. No? All right, so we're gonna have to just look at our toolbox and then pull out the correct tool. Well, try and pull out the correct tool. What do you see? What do you want to try with this? It's a U-sub, huh? It's a U-sub. Someone tell me how we know this. What was the clue to tell us that we're going to use a U-sub? Perfect. Yeah, the clue is that we have natural log right here. So clue. We take the derivative of natural log. It's this, yeah? And we see this 1 over x times dx thing over here, yeah? So it's giving us a fairly nice clue as to what form we should take. We should try a U-sub with this, yeah? So let u be natural log of x du by dx is just equal to 1 over x, that we just talked about. So du equals dx over x, and then we put it directly into this thing. Let's call this thing star. So star becomes the integral of 1 over square root of u du, and that's definitely progress. Now it's just a power in u, right? So that is just u to the minus 1 over 2 du. We ask ourselves, what do we differentiate to get to power minus a half? Well, we're going to differentiate u to a half, right? But if we differentiate u to a half, we're going to have a factor of a half in front, yeah? Which we don't want. So the antiderivative has to be equal to 2 u to the 1 over 2 plus constant c. Differentiate this, we will get that. Yeah? Then we turn it back into something involving x. This, power 1 over 2 plus constant c, and there we go. Yeah, this guy wasn't too bad. This wasn't too tricky. Let's do another one. As with all of this stuff, the more you practice this, the better you're going to get at it. And when you first, some of you have not seen that much calculus before, sometimes some of you have actually seen no calculus before. When you first do this, it might seem overwhelming. It might seem like it would be quite slow working your way through finding these right methods, but you're surprised how quickly you will pick up. So the graph of your acceleration or the graph of your progress will be like this. So it'll be slow for a fair bit, and then it's going to pick up quite dramatically. You have to get through this flat part where you're seeming to make very little progress. Each one of these questions will take you a fair bit of time, and then you'll just see that your brain will start to pick up these structures. It will seem like there's so many different things to try to begin with, but if you do this enough, you'll see there's actually not that many things to try. The structures will repeat over and over again. Okay, look at this. Any algebraic simplification we can do, turn this into a better form. What do you think? Yeah. So if not, what kind of form does this look at? What kind of thing do you want to do? Could do a u sub as 1 plus x. Yeah. Let's see what happens there. So if we let u be 1 plus x, then du equals dx. And then what happens to this? Then x is equal to u minus 1. And then we're going to have the square root of 1 minus this thing. So it's going to be 2 minus u over u du, which is this thing. Change times square root of 2 over u minus 1 du. Does that look better? Is it better, people? Is that progress? To me, it doesn't look much better. I don't know what form we could apply here. So maybe we could try a trig substitution, because it's a little bit, but I don't really want to do that because I have to think of 2 over u as being 2 over u square rooted squared, and I don't want to deal with square roots. So yeah, this isn't looking too promising. We keep fighting with this in this direction, or we could try something else. Which do you want to do? Do this if you want to keep fighting with this, or don't do this if you want to try something else. Okay, looks like no one wants to keep along this direction. All right, so let's backtrack. Look at this again. What can we do? Just I can't tell you to just speak because I can't identify who you are from a tiny box. So you're just gonna have to unmute and speak if you have a suggestion. Yeah, so trig subs are good when we have things like this. Trig subs are good when we have, let's put this in a little box, when we have either plus or minus a squared and plus or minus x squared. And if we break up the radical, we don't really see that. Yeah, I mean, we could give it a go, but I'm not sure it's going to go very far. But something has to work, right? So look, say it louder. Yeah. So we can always multiply something by 1, right? So let's call this thing star. So let's in here and go change method. So underline this guy. We're not going to keep going with this. Pen. It's not good. We could try algebraic simplification again. So if we look at this guy, 1 minus x over, 1 plus x. Let's try this guy. Let's do 1 minus x over 1 minus x. If we do that, what happens? Then this thing, this is just multiplying by 1, right? So on the top, we're getting rid of the square root. And on the bottom, let's put the square root, and then we have 1 plus x, 1 minus x dx, right? And then this is the difference of two squares, so this turns into this thing like this. Like this. Okay. Is that progress? Is that looking better? Why? What we want to do with this? Yeah, it's root, sorry. So it looks a lot better because I miswrote it. Let me ask the question again. Is this better? Now we do have something that looks like a trig sub, because 1 we can happily always call something. 1 squared is 1, so we can think of this guy 1 as being 1 squared, and obviously x squared. So we have this structure here for the trig sub. Yeah. So should we just do a trig sub? Hussein, let people give a suggestion. Should we just jump in here with the trig sub, or is anything else we should do before that? Right. So excellent. Yeah. So implicit in that is that you notice that if we do a u sub with 1 minus x squared, we're going to pick up the x dx, right? So let's break up this guy into this. Okay. And then minus this guy over here. And then this guy here is a perfect candidate for a u sub because we have the x dx, and if we just let u be 1 minus x squared, we're going to pick up a minus 2x dx, which is basically the same thing after we divide by this minus 2, and we can deal with this guy. So see what I mean? That this guy is now an easy problem. This is a standard u sub, yeah? Put your thumbs up if you're with me here. Okay, and then this guy here, this is indeed something we can do a trig sub with, or we can look at this and recognize it. Where have we seen this before? What do we know has antiderivative of 1 over square root of 1 minus x squared? Yeah, indeed. It is actually arcsine. It's arcsine. And this is implicit differentiation. You can quickly check this yourself. So if we let y of x equal arcsine of x, then sine of y of x is equal to x, and we differentiate both sides with cosine y of x. Y prime of x is equal to 1, right? And then we have that y prime of x equals 1 over cosine y of x. And then we want to understand what cosine y of x is. We draw a triangle which represents this particular thing right here, right? So we draw a triangle. So this is super fast. Maybe you're not going to get this as I do it right now. This is how I did this for my students from last section. again, I don't want you to memorize stuff. I want you to be able to work them out. So I'm going to quickly show you how you work it out. So look at this guy. We know what sine is. Sine is the opposite divided by hypotenuse. We put x here, we put 1 here. And then what can this thing be? This thing can only be 1 minus x squared. Yeah. So what is cosine? Cosine is the adjacent divided by hypotenuse. Yeah. So therefore, what is 1 over cosine? It is this thing over here. Yeah. So we can quickly figure out what this thing is. Yeah. So remembering its form, remembering that this thing might be the derivative of arc sine or arc cosine is what your memory should give you, but you don't need to remember which one. I don't want you to remember which one. I want you to be able to work it out rather quickly, rather easily. Huh? Anyway, so we know what this is. This thing is arc sine of x, and then this guy we're going to attack with the u sub. So if we let's put it down here because we're running out of space. So I'm going to let u be 1 minus x squared du over dx equals minus 2x, and therefore minus du over 2 equals x dx. Yeah. So then turn this stuff into 1 over square root of u. We replace the dx with this thing, or the x dx with this thing, but at the cost of having this minus a half here. So then this thing becomes plus 1 over 2. Yeah? And then this is all stuff we can calculate. So let me put a box around this, so we mix up what we're doing. So then this thing is arc sine of x. And then what's the antiderivative of this? It's going to be u to the power 1 over 2. And if we differentiate u to 1 over 2, actually we get exactly this thing. So that's the right thing. Plus constant c. Let's turn things back into x in one go. So we're running out of space. 1 minus x squared. So 1 over 2 plus constant c. And there we go. All right. Everybody with me? Okay, do this if anything's unclear. All right, let's recap the steps. How are we for time? Not much time. Let's recap the steps. What did we do? We looked at this guy. We tried some things. Didn't look any better. No? Then we backtracked. We backtrack. We look again. We must, well, maybe we've missed something. Huh? Someone came up with a suggestion of multiplying by conjugate, in other words, doing some algebraic simplification. That was the first step. That's what I asked you. And at that time, it didn't look like there was anything we could do. Yeah? And indeed, it's not that easy to see this. Yeah? But when we tried, we got nowhere. So either there's another method or we've missed the first step of simplifying by some algebra. And indeed, multiplying something by a conjugate with a square root, if you think about it, is not such an unusual thing to do. It's something we've encountered before. So we give that a go. We could have tried it with 1 plus x. It would be a little bit less simple. Or we do it with 1 minus x. So we do it with 1 minus x, and we turn into this. Yeah? And the guess of doing 1 minus x is, or the guess could be made because we could see that would have this structure, and this we would recognize as being in the form of a trig sub. This is indeed progress, but in fact we don't even need to do a trig sub because we know what this is. This is the antiderivative of arc sine. Start again. No, it's not. This is what we get when we differentiate arc sine. So the answer to this, when we try and find the primitive of this, it is arc sine. Yeah. So the main lesson, if there is a main lesson from this guy, is that you try something, doesn't work, you backtrack. Something you might have wanted to do before would have helped you. All right, so we're out of time, but I'm going to stick around and I'm going to do at least another problem because I want to show you some more and it'll be on the video. So feel free to leave, otherwise stay, and we will do some more of this. from the end of the section. So we have 4 to 1 log of y square root of y dy. All right. Solution. Give me a suggestion for this. This is indeed an integration by parts problem. What gives you the hint that integration by parts might be a good thing to do? Which one do you want to take the derivative of? Good. Yep. If we let this thing be u and this thing be v prime, then indeed we can easily take the derivative of u and the antiderivative of v prime, because v is just a power, v prime is just a power in y, right? And even better than that, if we quickly in our heads just try and get an idea what the form of u prime v is, u prime is 1 over y, right? And v prime is y to the 3 over 2 times 2 over 3. So when we multiply those things together, we have something which is just a power of y. Yep. And any power of y is an easy thing to integrate. So we see that if instead of dealing with u v prime, we deal with u prime v, we are in way better shape. Yeah? So this guy is indeed most naturally an integration by parts. Yeah? Cool. All right. It's 1 to 4. Okay. So integrate by parts. So this thing star is equal to the integral. Oops, not integral. Definite. Oops, this is 4 up here. We are going to put u and then v itself. So it's going to be log of y. And what's the antiderivative of v? We're going to have y to the 3 over 2 times 2 over 3. Yeah? And then minus 1 to 4. And then we differentiate u. We're going to have 1 over y. Antiderivative of this thing is again 2 over 3 y to the 3 over 2 dy, and then it's in a form we can do. So then let's evaluate this thing right here. We're going to have log of 4, pull out the 2 over 3, it's log of 4, and then square root of 4 is 2, and then 2 to the 3 is 8, so then this thing will be 8 like this. And then when we put 1 in this, log of 1 is 0, so that term we don't have to care about. And then this is the integral from 1 to 4. Let's pull out the constant of 2 over 3. And then it's just going to be square root of y, right? Because the powers cancel. So it's 2 over 3 log of, let's actually do this numbers. So it's going to be 16 over 3 log of 4. And then what is this thing? It's going to be minus 2 over 3. And antiderivative of, no, we've already done this. No, we haven't. Let's just erase this. This is 1 to 4. No, there we go. Like this. So then this thing, what power do we have? We have y to the 3 over 2, again, times 2 over 3. Like this thing. Then what is this? This is 16 over 3 log of 4. And we're going to have minus 4 over 9. And then we're going to have 8 here, because we're going to have 4 to the 3 over 2, square root again, 4 is 2, and then to the power of 3, it's 8. And then when we put 1 inside here, we just have this. So then this thing is 16 over 3 log of 4. And this is going to be 7 times 4, which is 28, right? So, right, 7, 14, 28, minus 28 over 9. Let's see if this is right. Yeah, this is right. All right. Everybody good? Yeah? Cool. You want to do another one? Yeah? Okay, we'll do a final one, and then we are done. Let's do this one. This one is trickier. So these problems get harder the further down you go. I think this is 43. Look at this. Yes, I mean, I see why you say that, but it's, again, so trig sub is when we have expressions like this, which is not quite what we have, so. A u sub with the square root, could try that. Yeah. So if we try it, what happens? U equals square root of x, then du by dx, 1 over 2 u, x minus 1 over 2. There's no way to, so this would be like 2 du is equal to x to minus 1 over 2 dx. There's no easy way to absorb that. Something else has to work. So the u sub isn't terrible because we could write this thing as x times x to the minus a half, and then turn everything in terms of u, and that would get rid of the square root. So that might make progress. That might be okay. But it wouldn't be a great expression. It would be like u squared on the bottom, u squared on the top, and it'd be one underneath would be 1 plus u to the power 6. It's not super, but it's something. So if there's in the list of the strategy things, one of the things like try all the natural things which you guys are trying. The u sub does make a bit of progress, but that's not the best way. And then after you've tried these natural things, you go back and you say, is there an integration by parts, a u sub that turns it into a different form, into an easier form? There is a u sub that turns it into an easier form. It's a little bit of a obscure one, a tricky one, but this is the guy. So let's underline this thing, because this will get somewhere, but it won't. This won't be the best way. So what if we take this? So let u be x to the 3 over 2. If we do this, then we have du by dx is 3 over 2, x to the 1 over 2. Yeah? So therefore, 2 over 3 du is equal to square root of x dx. Yeah? And then we see this square root of x dx stuff up here. Yeah? But the real thing that makes us happy is that we can write this 1 plus x to the power 3 now as 1 plus u squared. Yeah? So then the form of this guy, let's call this guy star. Well, so then star becomes 1 over 1 plus u squared. And that really does make us happy, because that is definitely simpler, and indeed, hopefully, this is recognizable for you people. Yeah, it's the derivative of arctan. Yeah, derivative of arctan. So then this thing is arctan of u plus constant c, and then we put it back. We have arctan of x to the 3 over 2 plus constant c. Yeah? So this was definitely hard. You have to look at this for a little bit or quite a long while perhaps, to pick up the fact that trying this means that this part gets simplified and we get to this. Huh? But once you have this idea, you can fairly quickly in your head see that it's going to make things better. Huh? So sometimes the U sub will be a kind of obscure, but it's there. There's always going to be a method there. Yeah? So the main thing is just to persist. And if you get something which is getting longer and longer and more complicated, it's probably not working out. It's probably not the right method. It might work eventually, but there will be something. There will be something inside these problems that allows you to do it reasonably easily. Yeah? So just have to pick it up. No, nothing as hard as this on a midterm. So you will have something from this section where they'll just present you with an integral. And it's a good guess that it's going to be a free response because there's multiple stages to do. But not of this level of difficulty. So the point of putting hard questions in the midterm is just to distinguish between the A and the B plus or the B level students, and at most there'll be 1 or 1.5 hard questions there. It's not most of the questions are entirely routine questions where it's very clear what you have to do. So you don't have to be able to do tricky things to get a very good grade. It's designed to be a course where you can get for sure a B plus by just doing the work, just being consistent, just being able to do all the straightforward questions correctly in the time. Yeah? This is by no means trying to present you with challenging exams to really spread out thinly the different levels of ability. We want to identify the A students or the B plus, but we want most people to be able to do this exam reasonably easily, reasonably straightforwardly. I hope you all want to get an A. I hope you all want to do as well as possible in this course and in all your other courses. But do not be intimidated by the harder problems. There'll be 1 at most or 1.5 at most. Okay, so let's wrap it up for today. Now is my office hour, so stick around if you have any questions. Otherwise, I will see you all on Friday. Have a good day. Mm-hmm.